Good evening, good evening to one and all. On the behalf of the Department of Electronics and Telecommunication Engineering and the entire organization committee, I, Professor Hemant Mahajan, extended a very warm and heartfelt welcome to today's resource person, Dr. Ashutosh Srivastav, to the fourth day session 7 of the AICTE Atal sponsor 6-day online faculty development program. Welcome, sir. Dr. Ashutosh Srivastav is an academic and research specialization in electronics and telecommunication engineering with a strong focus on the first participant studied solar cell absorbed material and thin film solar cell simulation. He holds a PhD in electronics and telecommunication engineering from the National Institute of Technology, NIT Silchar, where he conducted extensive research, novel quantitatively thin calculus and the device level simulations for the photovoltaic technology. He completed his MTech in the microelectronics and VLSI system design from NIT Mizoram and his BTech in electronics and communication engineering. Dr. Srivastav has authorized several scientific index journal publication in reputed international journals such as Solar Energy, Applied Physics, Advanced Theory and Simulation, and the Journal of Physics, Chemistry, etc. His research contribution also including the Australian pattern reflecting his involving the work on the thin film of the solar cell technology. He has represented his research multiple national and international conference contributing significant to the field of photovolatile semiconductor material and device modeling with expertise in the tool of the such as a WASP, then SCAPS 1D and Silvacon TCAD along with the proficiency in the Python programming. Dr. Srivastav integrated theoretically modeling with the computational simulation in his teaching research. He is currently servicing assistant profession School of Computer Science and Engineering Technology at Bennett University of Greater Noida. Previously, he worked as an assistant professor BV Raj Institute of Technology, Telangana. Dr. Srivastav is passionate about the academic research, collaborate learning, and mentoring the student in emerging areas including solar cell device, physics, DFT simulation, and advanced material of sustainability energy application. Thank you, sir. I request sir to start the session.
Thank you so much, Professor, for this warm welcome. And good
Yes,
evening
sir.
to one and all present here. Yes, sir. Thank you so much for this welcome, sir. So,
Yes, sir.
shall I start my session, sir?
Yes, sir. Yes, sir. Sure.
Okay, so let me share my screen first. So, I hope my screen is visible.
Yes, sir. Yes, sir. Is it visible?
Yeah. So, hello all participants. Thank you for coming this odd time at 7:30 in the evening for this session. Thank you all for coming. So we all are here for today's this. There's a whole FDP is based on solar cell, its simulations, and since it's the fourth day, I believe that most of the basic concepts have already been taken care of, which I can see in the schedule that everybody has taken a lot of efforts for this solar cell. I'm really obliged to the university for conducting this FDP, like specifically on solar cell, which is like first of the kind I have seen. So thank you, sir. Thank you, entire university, for conducting such good workshop and FDP on solar cells. I'm Dr. Ashutosh Srivastav, and today I'll be here for taking this software that is SCAPS 1D, which is like solar cell simulation software in one dimension. So before I start with uh, let me have a very quick recap of what this software is, and then we'll move on to how to work on this. So in my today's session, like I have two consecutive sessions today and tomorrow. So today I'll be more talking about how to use the software, where to download it from, what are the aspects of this software, alongside a very small example of mind paper only, like the work that I have done, just to make you all understand how this software work. And tomorrow we'll have some like session on how to use it on, like doing it on here only. Okay, so SCAPS 1D is basically a software wherein we can simulate specifically solar cell, like thin film solar cells. Okay, the name itself is solar cell capacitance simulator. And if you can see on the screen, the first line reads is to be one-dimensional solar cell simulation program. So basically, if you all remember that in this device simulations, there are certain Poisson's equations and continuity equations, and all these equations solves for three dimensions of the work. But as we feel that Professor Bergelwen, who is the professor in University of Gent in Belgium, he has developed this software, and he tested it for one dimensions only, and he found that in solar cell, even if we analyze the equations in one dimension, it gives a very good results in terms of the solar cell parameters. So if you all have ever worked with solar cell, there is one very good software, Silvaco TCAT, which works for three dimensions. So I personally myself has done a bit of work in Silvaco as well, and a lot of work in SCAPS. And the two software are very like similar in their results when talking about the parameters. So by this I mean to say that even if this software solves the equations in one dimension only, it is very well believed, and uh, in the community, in our community, it's established that we can use this software for doing lots of research and finding out some good work, so that we can develop our own solar cells with the good performances. And talking about this software, it was first developed by Professor Bergelman, who is a professor of grant in University of Gent, Belgium. He himself has started this software to work with copper indium selenide and cadmium telluride family. These two solar cell are basically, you say, this one generation. Like if you go with what different types of solar cells are, one of the type is thin film solar cells. So he developed this software to simulate thin film solar cells, because by the time we are in, mostly this industry is talking about silicon solar cells. But yes, a lot of research has been done, and we have found that this thin film solar cells also works very well. And in this domain, we have so far reached up to conversion efficiency of around 40 for perovskite solar cells, like which is a type of material which we use in this thin film solar cells. So I can show you the basics of this, what we call thin film solar cells. Like this, since this software talks about thin film solar cells, so just have a very quick recap of what exactly the thin film solar cell is and how does it all work. So if you can see this diagram, here we have basically two important layers. Actually here, if the device is fabricated in terms of layers, like first of all we have this absorber material alongside a buffer layer, and then we have a window layer. So you can see there are three layers which are in contact with each other, forming a thin film solar cell. So what are these layers? So one of the very basic layer is this absorber layer. So the purpose of this absorber layer is to absorb the photo, like this rays coming from solar, like sun. And here uh, there is a conversion of this electron hole pair, and it generates from where we can get this solar cell working. Then we have this buffer layer also. So buffer layer is basically a different type. Like if my absorber layer is mostly p-type material, then we choose buffer layer as n-type, so that there is a p-n junction formed at the junction. And then whenever the solar radiation falls on it, this electron hole pair gets generated, and then we just separate them across the circuit. We get this our work done, that we get solar energy, which is basically the conversion. Okay, now there are two more layers we can see here, window layer and like the contacts are basically the two electrical contacts which we have for any circuit to work in with devices. So this extra layer is window layer. Basically, this layer actually traps the solar energy or the solar rays, and it somehow helps in getting more and more pair of electron hole pair. So if we can see, there are two basic layers, absorber and buffer, which are actually important for generating electron hole pair and transmitting it throughout the circuit. But window layer is to get my solar cell, solar energy or solar rays trapped inside the solar cell, so that more of it get absorbed with the electron hole pair generation, and then which can be further taken to the contacts. So this is a very basic talk about solar cells, which is basically thin film solar cells. Now coming back to our software, which is SCAPS 1D. So I'll show how this software looks, and what parameters are required to put in to get our requirement. So if to start with, like whenever we do this simulation specifically for this solar cells, there are there are four parameters which we are interested in. Like we all must be knowing that when we are talking about solar cell, we need four parameters, and above all, there is efficiency. So we all work to get good efficiency, good which we all call as PCE, also power conversion efficiency. Then we also talk about how good the voltage generated, that is open circuit voltage, and then short circuit current. And so basically, we are interested in these four parameters when we simulate cells like solar cells. So for this software, uh, it has been started, I think 2002 around, and now in 2025 they have the most region. Like my slide doesn't talk about 2022; it is 2025. They have the latest version up to May 2025, which is CAPS 3.3.12. It started all from 3.1, and now within so many years and months, it has come up to this. So this software actually can take seven different semiconductor layers. Why semiconductor? Because since we are talking about solar cells, as for this thin film solar cells, we talked about absorber layer, and then buffer layer, and then window layer. All are these semiconductor layers. So this software gives you visibility to add seven different layers. Okay, I will be talking more and more only about these three layers, because since in solar cell, the work I have done so far is for these three layers. But if required, we can add seven layers. So basically, you may be thinking that why do we need seven layers when we can get the solar cell? So you all must have heard about tandem solar cells, like wherein we get two different solar cells attached together, and then the power conversion efficiency gets remarkably well. So to simulate such solar cells also, we can use SCAPS 1D. The SCAPS stand for Solar Cell Capacitance Simulator, okay? And 1D stands for one dimensional. Like here, the physics behind this software is to solve Poisson's and continuity equation, but only in one dimension, not in all the three, which is the basic nature of these two equations, okay? So if I can show you how this software look, so I'll be sharing. Okay, I have those screenshots here. I can move on. So yes, if you can see this, once you install the software, the primitive console looks like this. It will all will be looking like what it is all. So I'll show you how to like generate your device and how to simulate. Like when we talk about understanding any software for the first time, we must be knowing how to generate my device, which I means which we all will be simulating, and then how to give all the parameters, because simulation is all about telling the software the physics behind, which is already given by Professor Bergelman in his software. But the parameters that we are interested in, we have to give it on our own. Okay. So the main console looks like this. If we can see here, that set problem is there. From here we can get our device done. Okay, so you can see this console number one. So console number one is for generating your device. Like here, this three layer device, we can generate it from here. Then there is console. Actually, this is your complete console. I have divided it into four parts. So the second part is the action part. Like whenever we are simulating anything, we are interested in certain parameters. Like if we talk about solar cell, the IV characteristic that we all are aware of, IV characteristic is something that we are interested in, right? IV means current voltage graph. Okay. Also, if for further research, we can plot our CV plot also. CV stands for capacitance voltage plot. And then there is this CF plot, which is capacitance frequency plot. And the last one is quantum efficiency. Like, okay. So these four parameters we can get, or we are interested in to get from the software for simulating our own device, and the device is solar cell, and specifically this thin film solar cell. Okay, so if I can show you, this is one of my device that I have worked upon, and let me explain it a bit further. This you can see absorber layer, which I was talking in my previous diagram, and this is that buffer layer. Okay, so for my work, I have worked upon chalcogenide materials, which are actually thin film solar cell absorber materials. The best of them is this copper zinc tin sulfide, that is CZTS material. So it is very well established material which can give PCE of around 12%. So I worked upon improving the performance of this material. So my majorly work in my PhD is around for this uh, density functional theory. So that's a different case. Like I have worked upon this CZTS material and coined three, four different materials. One of them, the material is this AMTS, wherein this A stands for silver. So AMTS stands for A for silver, and then magnesium tin sulfide. So this is the material I have worked upon. So that material part is a different work of research. Once we get after my half of my PhD, I found that this material well aligns with CZTS. Now the other part of my work was to get this material simulated in a software like this SCAPS. So instead of using those CZTS material, which is well established material, I have used AMTS, which was the material I have coined in my PhD work. So now the question here is, uh, this AMTS will be working as absorber layer, and I have used zinc selenide, which is ZnSe, as the buffer layer. This third layer is ZnO, that is zinc oxide, which act as zinc oxide, which is window layer, which I talked earlier, that it's a layer that is responsible for trapping the sunlight, so that majorly electron hole pair gets generated, right? So these two layers are collectively window layer, and of course the whole structure is developed on a soda lime glass structure. Okay, like when we fabricate any solar cell, we always have a base material on which we fabricate our solar cell. So for our simulation we have used that soda lime glass. But when we simulate this structure, we do not use this soda lime glass properties. Now, one very good question that should come to your mind, that I'm repeatedly saying that we should simulate, simulate, simulate. But how this simulation will work? Basically, I have shown you there are three layers. Now, how my software will know that I am talking about AMTS, or I am talking about CZTS, or I am talking about silicon? Like, software doesn't know. Like, when we work like in generating the software fabrication, then we have those material. But how to get those software known that which material I am working with? So I hope this question must come to everybody who is learning the simulation. So how do we let the software know? By putting all the properties of a material which are required or which gets involved when talking about the material as a material in solar cell. Means, if you are using any material as a part of solar cell, some of its material properties will definitely be used in terms of it will get in contact with solar, like solar energy, and then electron hole pair generated. So all such parameters, if I feed my software that these values, just take these values and then do the simulation. So those values we need to put in our software. So if I'm saying that my software will be taking three layers, I have to put all those values which are important for any material to be used as a solar cell material. S- Say, for example, if I have to judge a material on its this thermodynamic properties and all, then certain different set of properties are required to be checked upon. But when we are talking about any material to be checked on their solar cell properties, we have different such properties which needs to be feeded in our software, so that the software now knows that I am dealing with a material which has these properties, and based on these properties my all the equations will be solved. Okay. So for those properties, I'll tell you what are those properties. Okay. So this was my first console. Then this is third part is this dark and light. So there are two such things. If you like, you must have studied in solar cell that solar cell works when we get its bombarded or in area of solar light. Like, whenever solar light falls on solar cell, it generates and all everything. So for our simulation also, I have to tell my software that my device is ready. Now give it the light. So how will we give the light? We will give that through this portal, like the third console, which I have divided here, but it is on your main console. So if we check on this light, then the software will provide all the properties of a solar light here. Okay. And the last one is this certain working point, like whenever we work with solar cell, it always work with open area. So that open area must have certain temperature, and then when you are connecting it through some this series resistance and shunt resistance, which are a different part. Like whenever we simulate any PN junction or any solar cell, automatically it has some series resistance and some shunt resistance. So whenever we do simulation, we need to tell our software that these are all the parameters that will definitely come into picture whenever we are imposing our device in the sunlight. Okay. Because the best values, the best performance from a simulator only comes when we make it more like a real value, which means that we have to give all the accurate values that are required for its simulation, be it any material properties, be it the sun rays, be it all the working parameters like series and shunt and everything. So all these parameters needs to be feeded to your software, so that you can get it, like you can get the simulation and your properties. So this is your first console. when you install this software, it will come. Now a question must also come to your mind, that how to get this software. So just for your information, Professor Bergelman has made this software open for all, and I must tell you that there are n number of students, PhD students, scholars abroad, in India and abroad. They are doing their complete PhD using this open software, because the results that we get from this software are so good that if you just check on solar energy, it's a very good journal in our field. There are n number of papers coming every year where the researchers are only focusing on this software. And I must tell you that I have worked with this software in 2018 to 22, and from 18 to 22 and from today in 25, there has been lot of changes and lots of improvement. So if any of you is willing to work upon solar cell, you can use this software because it is easily available and freely available on internet. All Professor Bergelman wants that whenever we are using his software, we just acknowledge him in our any publication, and also ask him not to get in any trading of money and all. This is all what he wants. That he clearly mentions. I'll share one of my story, that when I started working on the software, definitely you need to learn it. So I mailed Professor Bergelman that, sir, this is the software I got to know, and he has personally emailed that, yeah, these are the conditions, you can use it, but give me this acknowledgement at your whenever you get any publication. Definitely, I always give him this acknowledgement for his software. And so at the last, I'll provide you this link also where you can download this software. I have installed it in my system, and will definitely ask most of us, whosoever wants to work with, I'm open to all. Okay, so now my first this is the first console that you will come across. You now you want to design your device, that 3 layer 7 layer structures. So for that, you need to click on this set problem. Once you get this set problem, this console will come into picture. Like this part of solar cell will come on your screen. So if you can see again, it has been divided into 3 parts: first, second, and third. So this first part is whether you want to generate a new device, or you want to work upon any already existing device. Professor Virgilman also gave a few very good examples for any learner who is starting to learn the software. So in this load section, we can get all those devices fetched in our console, and then this save button is there. Once you do everything, it will be saved. Now you can see there are these 7 layers. You can see 1 2 3 4 5 6 7, and then these two are the contacts, this metallic contacts that we will work upon. Okay, there are interfaces also. Now definitely, whenever we get two materials in touch with each other, they always generate an interface. Like if I am having a material X and I am having a material Y, and if I make these two material in touch with each other, there will always be a thin interface created, and the physics of interface is very interesting and different. If you want your software, your solar cell to be simulated in a very real manner, we have to consider these interfaces also, right? Like in this example, you can see this tin sulfide and cadmium sulfide is there. So whenever a tin sulfide layer comes in contact with this cadmium sulfide layer, there is always a interface created, and the physics of this interface actually changes the dynamics of the working of the solar cell. Okay, so we need to feed certain properties which are required for interface to put their effort, put their physics in the working of solar cell. So basically, we have these layers. We can name this, like it is SNS. I can name is my name is Ashutosh. That hardly matters. But of course, Ashutosh cannot be a material. So since tin sulfide is a material, cadmium sulfide, and this and all are materials. So how my software will know that this is tin sulfide, this is cadmium sulfide? So definitely we need to feed on certain properties of the materials in the software. Okay, now how will we do that? So if we click any of these material, another layer of software will come in, this one. So once you click on any of these layer, which you really need to click on all the layers one by one. Okay. So let us start with one of these layer, that is tin sulfide. Okay. So I checked on this tin sulfide, and this console came into picture. I'll try to drag it a bit. Okay, okay, okay. For you people, it will be visible. I forgot that the screen is mine only. Okay. So you can see here there is layer one, like the name of the layer. There are 7 such layers, so you can add properties to all such layers. So I have named that layer as SNS. This is clickable, so you can click on it and rename it. You can rename it as cadmium sulfide, you can rename it as silicon. But if you do not change the material remains the same, no matter what the name you are entering. Okay, because this software does not fetch the material properties from internet. No, you need to feed on the properties of the material. So whatever material you are using, you really need to work upon the material, go for the literature survey, and get all these properties of the materials jotted down for your work. So, like since we are working for solar cell, so for any material to be used as a solar cell material in SCAPS software, we need 6 or 7 properties. One of the basic property which is very important is the band gap. Like the band gap of the material you need to work upon, you need to find it out. If it is a novel material, like for my PhD work, the material I was working with, that was something that was not there in any literature. I worked upon it. I like there's another software called as WASP, which works on density function theory. So there I got these such certain materials. So I need to calculate these properties for the material. So I calculate the band gap. So if you are using any existing material, like when we are working with device, we always work upon any material which is already existing. Like we do not put our research in finding the new material. So we need to get this band gap, and then electron affinity, and then dielectric permittivity of that material, and then conduction band effective density of states, and same way valence band effective density of states. Then it's the electron thermal velocity and hole thermal velocity, and lastly this electron and hole mobility. Okay, after that, this doping concentration, like if your material is p type or n type, depending on that you can have this nd and na, that we all are aware that nd is the donor density and na is the acceptor density. So these are very important properties that we need to have these all. So and many times it becomes very easy for us if we get any research paper based on the materials that we are interested in taking in our software. So these properties align with this tin sulfide. Okay, so to get this software work, we need to put all these 8 or 9 properties in our like we need to get it and then feed it here in the software. Okay, after that, if you can see the right section, there is this defect 1 and defect 2 and this and that. Okay, so this is the property of the material. Now, does any material exist without any defect? Like if we talk about the basics of any material, be it what, be it silicon, be it germanium, be it gallium arsenide, be it CZT, or whatsoever it is, every material has certain sort of defects in it, which is the fundamental defects which already exist. Now, to make my software, like a very good example is that if you are hiring a teacher to teach your kid or your ward, you need to tell the teacher that these are the good thing, these are the bad thing, these are the things associated with your kid. Then only the teacher can understand how to go on. Similar way, this software will only give you the exact simulation results only and only when you give all the real properties as well as certain problems also that associate with the material. Like, let us say that silicon, for example, silicon is a material which easily gets heated up. So we cannot underestimate this property, or we cannot just leave this property when dealing with silicon material as a solar cell device material. Because when we work with solar cell materials, all the good and bad properties needs to be taken care of, right? So in this software we can make all these defects also there. Okay, so there are he has given 7 different defects possibilities. So you can add 1 defect, 2 defect, 3 defect, depending on what kind of material you are using. So, and the question again will be how to add the defect. So again, if you can click on this defect, you will get this. So basically, what does defects do? Like when we are interested in solar cell simulations, defect is something that traps my electron hole pair. That is the only thing that the defects can do. Like let's say at my PN junction, which was my absorber and buffer layer, a certain electron hole pair gets generated, and due to these defects, this electron and hole gets trapped there. So that is something which is causing redundancy in our power conversion efficiency. Okay, so we need to make it clear to the software that there are certain defects which is by default present in this material, so you need to take care of these properties as well. Okay, so these 3 4 properties of those defects needs to be given here. I'll show you how to and what to, like how to add this defect and what are the properties that we need to put in there. Okay, so this way we can add defect 1 2 3 and all whatever you require. Okay, so after this, we have to click on accept. Accept means yes, I have accepted this material with these all properties which are good, and all these defects which are not bad, but yeah, they exist with the material. We cannot ignore them. Okay, so likewise, like once we do accept, again we will go for this window. Now again for this window, we have done this all changes for tin sulfide. So one by one, we can make changes for all these layers. Okay, somebody. Okay, no issues. Okay, so all these layers properties can be one by one entered, and then we can start the simulation. So after this, what screen will come? Okay. Now, once everything is done, you will come on again this console. Like you entered this console with set problem. You put all the values of your software, like, sorry, all your materials like 3 4 whatever level, whatever number of layers you're using in your device. You will add out properties of all, and then you will come back to this console. Automatically, it will come back here. Now, what you are interested in, since you are simulating a device for its solar cell parameters. So what are those parameters? Power conversion efficiency, and this open circuit voltage, then short circuit current. Okay, so for that I'm interested in IV means current voltage curve. Okay, so I will check on. You need to check on which property you are, which simulation you are interested in. Are you interested in IV characteristic? If you are interested in CV, CF, or you are interested in quantum efficiency. Okay. Now let us say for a very user learner like who is learning for the first time, I must say that at least 3 4 5 people among all the listeners must check this, although that will be very helpful that if there is any scholar who is working with MTech or PhD or some BTech scholars as well, if they really want to work with solar cell, they must try this software. It is very useful, free of cost, and your research will definitely grow on because the results that the software gives are accepted by our research community on a very well basis. Okay, so like okay, sorry, I somehow okay. So let's say I'm interested in getting the IV characteristic, like which is the mm, mm, graph that everybody of us are interested in when we are talking about solar cells. Okay, so I will check on this IV, and then I'll check on this IV, and then this calculate single shot will pop up. Like if for now, if you can see when I have taken this screenshot, it was not there. Means it is not there. Why? Because I haven't checked on these properties. I'll check on IV. Okay, before that, I told you earlier that since you are doing solar cell simulation, you must tell the software that my device is ready. Now you need to give it the light, the simulated light, like the artificial presence of light, so that I can get all my properties I'm interested in to work on. Okay, so I'll click on this light, like it's a check on button. I'll check it here, so it will come to light. Now there are lots of default values. Like when we start learning this software, most of the properties which we just leave on the standard values, like whatsoever the standard values put in by Professor Virgilman, we just worked on it because he has worked for a very similar, like in solar cell we do not change such properties a lot. Okay, so this temperature, voltage, frequency and all, so these points we will leave on in the same standard values. This series and shunt resistance, again I would say that these are the properties that gets associated with any solar cell you work upon. Okay, so you cannot ignore these properties. I'll show you that if I do not check on these two buttons, the the parameters that I'll get will be somehow different and may not be accurate, other than the properties, and when we check it we get a good values. Okay, so this is all the very basic. Like this session was to introduce you all for this very like good SCAPS software. So I'm not going much in detail at a very first point. Tomorrow we'll look into what are the technicalities behind, and we'll do certain simulations as well. Okay, so again, once again, we started with the device formulation by going into the set problem. There we got all these structures. We put on our parameter values. We put on our interfaces values. We put on our defects values, and then we came back to this set problem. Now here we checked on this light, and then I'm interested in getting the IV characteristics of my certain device. Okay, and then this calculate single shot will come into picture, like it will be popped up, and you can now click upon it. Like before, until unless you are not checking on any of these actions, it will not pop up. Once you get it, it will be popped up, and then you can click on a single shot. Okay, so I need to show you the software. I'll share my screen to the software part. There I'll show you how like these three things that I have discussed so far, and then we will move on to some other part. I hope my screen has been changed. Now from this PPT version, it must have come to this software part. Can anybody respond
Yes,
and
sir.
yeah,
Yes, sir.
thank you.
Yes.
Thank you. So you can see those screenshots in my PPT exactly are the same here. Okay, so since I have already checked on this IV, I'll not check it. So you can see this complete console. It is the console number one where we can just make our device. Then this is number two, number three, and number four. Let's start from the very initial set problem. I'll go with this set problem. I have already, I told you that my PhD, half of my PhD was on simulation of these devices. So I've already made this structure. I have already simulated it. If I can show you here, that one is this p-type material, then other is n-type. This p-type is absorber material, Then it is my absorber. Sorry. This is my buffer layer, and these two are my window layers. Okay, so I do only need these four layers in my structure. If at all you are working with any device wherein you need more than four, five, or whatsoever, you can add it. And I also added this inter. Okay, let me start with for the very first. So I can make it new. I will not make it new here. I'll do in my second session, that is tomorrow. Today I'm showing you how I have all done. So I have taken this load, and this will show you all SCAPS related devices that you have, that is already there in your system. So if you can see, this is one of my research folder only. So from there, I have one such device I can click. So basically, whenever you create any device in this software, that comes with the .def extension. So I can just load it. So you can see I have loaded it, and this device comes here. Okay. Now, like I told you that one by one, I have to enter all the material properties of the materials that I am using here. So I was using this AMTS, which is a silver magnesium tin sulfide. So once you click it, the same console will come. I told you, I have shown you earlier in my PPT as well. You just see it here. This is layer one. I named it PAMTS. If you can see, I can name it anything. Okay, but definitely we should not do this. We just name it the same. Okay. Okay. One thing I forgot to tell you all while I was doing my PPT. These are properties we talked about. Band gap. So this material I coined, and this material was having a band gap of 1.631. I got this property from density functional theory simulations like DFT, which we also called as first principle calculations. Okay, but if you are using any well-established material, you will definitely get that it's a band gap. Then electron affinity, and you can see if it is 1.6.3. So I can change it. Sorry. So I'm adding 1.631. So this is my band gap, which comes with the electron volt. Then electron affinity. This is very similar to the parent CZTS material. Then dielectric permittivity I have calculated in my DFT simulations. Then as this CB and VB, like conduction band effective density of states and valence band effective density of states. Sorry. After that, we need to enter the thermal velocity, which is very mostly certain to the power of 7. So although I have calculated it here, but you can get it for any material you want to work with. You will get its value. And then now, in the initial, if you can see that this is AMTS is a p-type material. So if it is p-type material, it will be having acceptor densities. So acceptor density I have put 5 raised to the power 15. And since my material is p-type material, I am putting ND as 0. Okay. Now, sorry, I have just switched off my video because there was certain internet issue, I believe. So it may not hamper our talk. Okay. So this is, yeah. This is all material I have entered. Now I was talking about to make the software understand my material more effectively. I have added two defects. If you can see, defect number 1 and defect number 2. So there are certain properties for this material. So since I have already added it, I can put on edit. Like if you can see this, add a defect 4. I have added 3 defects. So there are 3 tabs available. I can add certain more also. So once you do it for the very first time, this add a defect will be here. So I can edit it also. If I will click upon it, you can see another window pop up, like your previous console will be there at your desk, but another this window will also come. Now this ask about what type of defect you are interested in. So they have given so far neutral defect, single donor, single acceptor, double donor, double acceptor, amphoteric, and custom defined multi-level. Okay, so these are some standard defects that needs to be like added here. So by default, I have taken one neutral, one n-type, and one p-type for my material simulations. You can go through some literature to get to know what kind of defects that your material will be having once you get the simulations. Then this capture cross section of electrons and capture cross sections of holes. It's a velocity per section unit section area of electrons and holes that you need to find it out. But if you just put it on whatever the standard values that Professor Bergelman has entered, which is the standard values of electrons and holes, you can get the simulation done. Then, of course, if you remember the band diagram of any PN junction, there are two valence. One is valence band, and then the other is conduction band, and in between there are certain bands wherein we get our defects, defect bands. Defect bands can be nearby our conduction band or can be nearby our valence band. Okay, so you need to define that where does your single energy distribution is like. So it can have a single Gaussian uniform or this conduction band tail form or valence band tail form. So I did it for single. I can use it Gaussian also. I have seen some one of my paper I've used uniform also, that you can change. Now they ask that where does your defect lie with reference to energy level. Okay, so we put in normal zero point 0.6. Okay, then what is the density of your this defect, that how likely your defect is there and how much is there, so that we need to tell to the software so that we can get maximum amount of good. Okay, so once we do all these changes and everything, we can rename this defect also. We can accept it. Likewise, you can add 1, 2, 3. For my work, for my material, I have used these three defects for this particular AMTS material. Okay, once you do it all, just a second. Okay, so actually it was in complete mode, so I was not able to see this accept. So once you do this all, you just put click on accept button. So accept button tells that all properties related to that material is now being given to the software. So for me, I have added this AMTS. Likewise, you can add, okay, one more thing I forgot again. One thickness. When we talk about thin film solar cells, thickness is very important. That how wide or how thick the material you are using in. So and by default, this value comes in microns. So let's say you want to work with a device wherein you are entering your this materials with nano meters length or picometer, whatsoever you want. So you first need to convert that into micrometer, because the standard value that they are entering here is in microns. Okay, so for my material AMTS, I have entered 2 micron, that is 2.000. You can add it, you can enter any of these. Okay, one more thing is there, uniform pure. Like I have used a material which is purely P type, and so there is no any change in its properties. But there can be certain materials which are not purely A, or which lies in between 0 to 1, or the properties changing linearly or parabolically or logarithmically or exponentially or a beta function or power law or from a given file. If you want to define your material whose properties vary with this sort of, you can add the file. Okay. So, but for my simulation, I have used a pure A material, which is my pure AMTS material. Okay. So, yes, this is they are telling that since I have clicked upon it, so they are saying that the grading settings will be defect. I said yes, no problem, because I have used the same. Okay, so this I was interested in, like to tell you all that this material is material's thickness is important to enter, and I have entered it to be 2 microns. So if you're entering anything in nanos or any other, you need to convert that into a given micrometers. Okay, then everything is same. I'll go with this except now my one material is somehow entered in this layer. Then likewise we can add for another material. Here also I have added only two defects. The difference here will be, now this material is n type, so it will have donor density instead of having this acceptor density, right? So we will have this donor density here, and all these properties again I have obtained it. It is a very well known material, so I have also used the properties from literature, and then again I have added these defects and all. So except, so likewise there were four such layers I have added them all. Okay, so one by one, you will add them all. Now my all four layers have been added here. Now my interest here in to add the interfaces. I told you that whenever two materials come in contact with each other, there is always a new physics coming into the picture, which is the interfacial physics. Okay, he has muted himself. So for me, the material was AMTS and ZNSC. So these two interfaces we were interested in because it somehow affects the property or the performance of my device. So I have considered that there exists an interface in between the two materials, which was AMTS and zinc selenite, and I have added one of such interfacial defects. Yeah, whenever you talk about interfaces, it must have a defect because interface will have a defect. So that defect I have defined here. So now again, how will you add it? There is defect 1, defect 2, defect 3. They have somehow up to the defect 3. You will click on defect, again a new window will pop up. Okay, so you can change all the properties of this interfacial defect. Okay, but the standards for entering will be the same. Again, what kind of defect type you are having, how is your capture cross section for the two varies, and then what is the energy distribution. Okay, so one by one everything is there, and at the last you have to put on accept. Okay, once again it is there, and once you do all the changes, like this change were in reference to the interfaces that will be created, you have to put on accept. So as of now I have formulated my device. मतलब मैंने अपना सोलर सेल क्रिएट कर लिया. Okay, so basically my solar cell was consisting of one n type, one p type, and then another zinc oxide layer. You can add up to 7 layers, but not beyond that. Sorry. So this all I have added. Now how my simulation will go ahead, you can visualize. I have got one hands-on with Mr. Suresh. So sir, do you have any question or what? Or if you have, we can just have your question here. Okay, maybe by mistake that hands-on was there. No issues. Okay, so okay, so I have added this all. Now you on the right hand side, you can see that your device is somehow in terms of its structure, like fabricated structure will come just for your visualization. Okay. So Rahul sir is asking me, Rahul Kumar, sir, what is the optimal value? Yeah, very good question. Actually, I was just seeking that somebody should ask me this question. Optimal value is like, with this caps, we optimize our device, like, depending on what different type of material you are using, the thickness will vary. Like, for talking about my research that I have made around 10 to 15 such devices, the minimal I had used was 1 micron, and the maximum I have used is 3.5. But 3.5 is very high, which was a very, but on an average it lies between 1 to 3 for CZTS material, I'll say. I'm not sure about the other materials. So that is the beauty of the software, that once you enter all the properties, you can optimize your device. Optimization means, like, first you will click on 1 micron. I'll show you. I'll show you how can we optimize. I'll show you, this is my optimized device. I'll show you the property, and then we can change. We will keep on changing these values. Like, I'll put 1, then 1.5, then 2, then 3. Maybe I can add 2.2. So, and then we will see what is my all those four parameters values are. Once you get a stagnant value for a certain thickness, you will find that this is the optimized thickness for this structure. A very good question it was, that since we are working with thin film solar cells, the basic optimization of the device is done for the thickness. So let's say I have, for this material it was, I think, 2. Okay. So with 2, it is okay. Now I will put it okay. So my device has been formulated, and now you can see calculate single shot is there. Now what I'll do, I'll just add light here, and I'm interested in IV. Okay. Now, if I'm interested in IV, just see the columns corresponding is V1 to V2, and stop after VOC. What is this? I'll tell you the meaning of this later on. Just let's get it simulated. So I'll do calculate single shot. Now, since I have checked on IV button, the results of the calculation will show me only IV, right? So I'll put it here, calculate single shot. Now, if you can see, my real-time band diagram is changing, and then lots of changes are being done. Its current density and all. Okay, so yes, this is my simulated result. At this point of time, we'll not talk about these four graphs. This I'll take care tomorrow. But yeah, let's start with what I have checked is was IV characteristics. So I'll click on IV. Okay. So this is the IV curve I got. It is very fine curve. You don't see that I have added a normal values and I got it. No, the device that I have shown you all here was my optimized device. Like, all the values I have optimized, and finally, so this was one of my papers output, that was 19.2% efficiency is there. Fill factor I got it was 76, and VOC is 1.11, and JSC was 22. So the all four values were quite good with this optimization. Okay. Now, I'll show you that once, like, let's say this is not the optimized. Let's say I have entered the basic properties. Basic properties means the properties which will not change with the material. Like, if I have chosen a X material, all of its properties are now deadlocked. Like, I am bound to use that band gap. I am bound to use that recombination coefficient. I am bound to use all this density, velocity, everything. But one thing that can be changed is the thickness. Thickness is something that I have to enter. Like, so again, I'll go back to the action. I'll set problem. Same device is there. I'll change my thickness. Let's say 1.5, and everything is same. I'm not changing anything except, and then here I'll also accept. Okay. If you remember, the 19.6 was there, right? 19.6 was my uh, mm, PCE, power conversion efficiency. Okay. Now again, I'll do this calculate single shot. Now it's a real time picture. We can make a video of it, and it really looks beautiful to see your this band diagram being formed. Like at the interfaces, there is a lot of changes, and you can just plot it later also. Okay. Now I have changed. Then definitely my values. How to check your values? Go on IV. On the right hand side, you will see this IV. Just go on it, and you can see that now my efficiency has dropped from 19.6 to 19.00. Okay, so now you can say that since why I have used that 2, because with 1.5 my efficiency was 19, but for 2 my efficiency is quite like has been improving. Okay, and if you do not remove your previous simulation, I'll show you where it is. So you can see there are two graphs. One is this purple color and the other is this blue color. So purple is my previous one, and this blue one is my current one. So you can see that this curve is quite square shape. If you somehow have studied how does cell thickness affects temperature rise in photovoltaic modules. Okay. So your question is temperature effect. Sorry. Can I see the question once? How does your thickness vary the temperature? Okay. So thickness vary. The what temperature you are talking about? Since we are working with solar cell, so the temperature is the outside temperature. So what temperature you are interested in? Can you just elaborate your question, please? Ambient. Okay, so you are interested in how does, of course, if there is okay, no ambient. If you're talking about solar cell will have the temperature around by the solar energy only. Okay, so once we are in, but yeah, you can say when we increase the this thickness, the internal physics goes beyond something, and there will be more of this electron hole pair generation. So yes, more electron hole pair generated, the circuit will flow, the current will flow definitely. If current increases, somehow your temperature also increases because the temperature goes directly proportional with the current. Okay, so definitely the moment you increase the thickness, the ambient temperature will increase. I hope I was clear with my explanation. Yeah, I
Sir,
was clear.
I'm asking if the temperature, atmospheric temperature is increases, so that will have any effect on the output or efficiency of the solar cell
Yes,
because
yes,
thickness.
definitely.
Ah, yes, sir, that is
Definitely
what.
it will have. Definitely it will have. That's why I can show you in your on my our console. Let it put it action. You can see here temperature is there. One of my findings of my work was to check the final output based on this temperature. So if you will change this temperature, it will show defect on your efficiency also. Definitely do change. Okay.
Yes, sir.
So
Thank you, sir. Yes, sir.
yeah. Now coming back to my console, yeah. So you can see here V1 and V2. So these are when we do simulations, we reach up to VOC. So if I don't change, this V1 is there from where my simulation will start, and V2 is up to where my simulation will go. And if I check on stop after VOC, so basically when you are simulating your solar cell, once the open circuit voltage is reached, it will show you the best performance. Like if the amount of solar energy or the performance is not good, the device will not reach to its VOC. It will not show you the complete efficiency. So by default, if I check it, by default it comes to zero point 0.8. Okay, If you will not check, what will happen, that your simulation will work only up to the like the voltage difference of zero point 0.8. And if this is not your VOC, your simulation is not good. So again, how will you know that whether you have reached your VOC or not? So that is a hit and trial method. By default it is zero point 0.8. I'll put it 1, and let's do the single shot. So you will find that your work is like your simulations are not quite good. It is done. So you just see these red marks. This red mark shows that your simulation is not correct. Why? Because you have the simulation has not reached its VOC. So these values are not correct. So this red color at the downside are very important for us to understand. What I need to do, then again I'll go here and I'll try for anything in between. Let me put it 2.0. But 2.0, and I'll check on this stop after VOC. So once the VOC is approached or reached, the simulation will stop. And now I'll get this calculate single shot. Now you see there is no any red mark is there, and if you can see that fill factor has quite improved from it was earlier 60 something 65. Now you can understand that how simulation, this is your correct simulation. Why? Because there is no any red mark, which means that your efficiency is like your calculated parameters are good. So let's say if you get very good high efficiency, but you're getting red marks at the bottom, then you need to check on your software, check on your calculation simulation that there is something wrong in your certain values like that V1 to V2 after VOC. So I'll go back and okay. Now along with IV, let's say I'm interested in getting my CV curve also. CV curve is basically the capacitance voltage curve, and I can go with single shot. So simulation is going on. Maybe it will show you some other aspect also, which I wanted to tell you. That sometimes, but simulations works on like the physics defined at the back end. If my simulation does not converge, then it will show you error. Okay, and in that case, none of the properties like these all four parameters will not be calculated. You need to check on the input value. So I believe that certain problem has come. That's why this is continuously. Yeah, I'll go on for my CV curve. So you can see this is your 1 by C2 versus your voltage. So this is not quite good. It's almost showing you a straight line, which means that I need to put on some uh, certain different values. Okay, so that also you can change it from here. We can make it from -1 to 1. Okay, you can make it to 1.5, and then let's okay. One thing I was telling that if you do not click on this clear all simulations, your all simulations will come one over the other. So if you want all the simulations, then you can keep it. Otherwise, if you are simulating for every new time, then you need to do it clear all simulations. So what it will do, it will clear all the previous simulations. Now whatever results you will get, that will be entirely based on the simulation you are doing for the current device. Okay, calculate single shot. Meanwhile, I can see that somebody has asked something. What? Are parameters set by trial and error methods? Yes. Trial and error methods only for your device thickness and these VOC and then this CV curve. All these are hit and trial method, trial and error method. But the basic properties of the material are not to be hit and trial. That needs to be very specific that the material has. That's why this optimization we do it here this way. We can put it on some. Sir, at what temperature SCAPS 20 calculates result? It is at 300 K. You can see. I'll show you. Okay, I mean, like once whenever your simulation is running, it will not take any other action. Okay, so now you can see my CV curve is quite good. You can see this one. This is reverse. This is my CV curve. Okay. So anybody was asking at what time? Just see, it is by default they take it at room temperature, but it is 300 Kelvin. Like we assume that whichever solar cell you are interested in or working with has to work on this room temperature. That's why it is here. So you can now see that we can get the basic four properties, the CF, then you can get this CF, then quantum efficiency also. Okay, one more thing. When we go for CV or CF or QV, by default IV is calculated. Okay, so CF I can also show you. These are your CF values, capacitance versus frequency. So of course you need to identify, you need to know the physics, you need to explain this, why is it all happening and why not. So that's a part. So you can see that for one device, for one click simulation, you have so many results that you can analyze, that you can work on, and get your work published. So frankly speaking, this software is very very good to enhance your knowledge for solar cells. Like on a contrary, if you any of you have worked with Silvaco TCAT, which is also a very noted software for device simulations, but when talking about solar cells, it doesn't give these many calculations right at your hand. So for there, like to get these all calculations, all this analysis, you need to work upon your data that you receive from Silvaco simulations. But here Professor Bergelman has added all these physics in the software itself, and and accordingly there are lots of like analysis. I can show you energy bands are there, then generation recombinations are there. You can see how the carriers are generated and all, and this all different like electron hole pair generation is there. You can add on all these simulations to make your simulation more real and all. So, of course, a lot of literature is required, a lot of study is required to understand your device, and whatsoever it is required for solar cell simulations, you will get it here in SCAPS 1D. So, like to various researchers who are like doing part-time PhD or doing part-time MTech or are associated with any institution wherein we are not getting Silvaco, which is definitely it's a paid software and highly paid software, which we cannot afford, of course, being a single researcher. So we can work upon this software and get our publications done and get our PhD defended and all. Of course, for MTech, I have guided so many MTech students who have done their work in this, and a lot of BTech students also. I myself has done my PhD, 20% of my PhD on this software. So yeah, it is good one. So you can definitely work upon it and think of it doing it this way. So at the last of today's session, I'll tell you from where to download this software. It's very important. So okay, I'll share it again. I'll share my different screen. I hope the screen is visible. You can see scaps.ellis.ugent.be, which is SCAPS official website, which is from University of Gent. And so here, this is the complete information about the software. You can see that there has been lots and lots of improvement in the software. The very first software they have started was SCAPS 2.0, and nowadays they are entered into SCAPS 3.3.11. Okay, which was 2024, and then it has been somehow improved in 2025 as well. So the most, you can see the most recent versions, CAPS 3.8 May 2020. Okay, no, it's not May 2020. They may have used some. Okay, so this is the website from where you can get the information for the software. Now, what I have observed that Professor Bergelman has now removed that download portion here. Like he said that if you want to use the software, please draft me a mail. I'll send you this download link. And for myself also, when I started in 2018, it was available here in a public domain. We can download, but later on, for one of my student, I was thinking of downloading it, and then I couldn't get that uh, this version. So I mailed professor, and he mailed me back the version. So yeah, you can see Professor Mark Bergelman. He is professor in University of Gent, Berkeley, sorry, Belgium. Sorry, it's in Belgium, and he's work in electronics and information system. So basically, he will share where to download the software from. But for now, if you at all need where to download it, I have that software with me. So I will definitely share this tomorrow at the end of tomorrow, but maybe today also, so that by tomorrow you all can come up with uh, installing the software in your system, and then you can ask me. So I'll share another link. Okay, I have that with me. Oh, I have put it in my software. No, it is not there. Okay, just give me a minute. I'll uh, just a couple of minutes. Okay, that's in my PPT as well, I guess. Just check once. And if I have it, I'll share it with you people. So from there, you can download the software. Okay, no, it is not there. Just give me a minute. Sorry for this delay. Just give me a minute. Yeah, I have this link. I'll share this link here. But again, it is my humble request, whosoever will be please using the software or is interested in doing any research, please acknowledge Professor Bergelman. I have shared that link in my text. You can check it there. It's a link where you can get the software, all the previous versions and the new version as well. So I'll request you all to please kindly get it installed in your. It's just a 50 MB software. You can install it in anywhere, C drive or D drive or in your desktop as well, and just try to have certain simulations that are already inbuilt there, like there in the load section. You can, when you just click on load, you will get some examples there. From there you can get it. So please install this software and try to work on. Tomorrow we'll like focus more on the other part of simulations as well. Okay. So I hope it was all informative. Thank you all for listening to me. Yeah, Professor Hemant sir is there. Yes, sir.
Yes, sir. Yes, sir.
So that's all for the day. We can continue from here onwards to my tomorrow's session. That was some 7:30 to 9 from tomorrow itself, right?
Yes, sir. Yes, sir.
Yes, sir. Okay. Thank you
Okay,
all.
sir. Okay. Thank you, sir. On behalf of management, principal, and Atal FDP organization team, AC Patil College of Engineering, I express my deepest gratitude toward the Dr. Ashutosh Srivastav, sir. His talk will greatly benefit researchers and professionals, those are working on computational work in photovoltaic area. Thank you, sir. We'll meet again tomorrow.
Yes, sir. Thank you. Thank you, everyone. Thank you, sir. Good night.
Thank you, sir.
Thank you, sir.
Amul, sir.